Hello and welcome to this fourth episode of a base builder tutorial. And today we're finally going to start working in SpriteKit so we can finally show the world we're creating. And to do that, we will be importing some graphics assets that we need. The link will be in the description below. We will create a world visualizer. This will be a tile sprite manager. We'll create a sample world to show and implement the game loop so we can react to changes in the world. And a bit more about the Tile Sprite Manager. This one will conform to a Sprite Manager protocol, and that protocol will describe everything that's similar in behavior between the Tile Sprite Manager, but also the future Sprite Managers we will use to display entities and to display items of our world on the screen. The Tile Sprite Manager will redraw all tiles in the world whenever it's demanded. It will take care of caching for both sprites as well as nodes, and it will take care of what I call continuous walls. And this basically means that if you have a wall, we look at where it continues through, and we use a naming convention to describe in which way they continue. So we have a wall here, or a piece of wall that only continues to the east side. So we put in an E. This one has both an E and a west. We put in an E and a W. And basically we can compose the walls of the various exits this way. And if you take that naming into account, then we can build nice and continuous walls. So let's get started. I already started up Xcode, and let's start by first importing our graphics assets. So let me find them real quickly. I have a folder full of sprites here, and this one you get if you unpack the linked file. And this one contains, as you can see, all the various sprites as well as the walls with the various names and some additional stuff. So that's the first step. We now have the sprites we require to show a world. So let's start by first creating the Sprite Manager protocol. And this will be a Swift file called the Sprite Manager. And I will also create a new group called View, because this is all about show the world, and I'll put the Sprite Manager protocol in View. And this protocol requires to SpriteKit. There will be a protocol called Sprite Manager, and it will have cell size. This is how big a specific tile in the world is in pixels. And this will be a read-only property. Also, it will have a Z position, and this is what we can use if we have multiple things we want to show on the sim location. In what order do they get shown? And higher values get higher priority to be shown. This too is a read-only property. And for now, this protocol has only one requirement called a function called redraw, and we redraw the world in a scene. It's an SK scene. And that's it for the protocol so far. Now let's create a concrete implementation, and that will be our Tile Sprite Manager. I'll also put it in the View folder. It too requires SpriteKit, and it will be a final class, Tile Sprite Manager, and this will be Sprite Manager, and it will take a Z position, and cell size. These are requirements from the protocol. And we will create two dictionaries. We will create a tile texture map. This will be a cache. This will translate a name of a sprite or a texture into an actual texture. This way we can reuse the same texture for each and every one of the same tiles on the screen. And we will also have a tile sprite map that maps from a location to the SpriteKit node that displays that location. Then we'll create an initializer with a cell size and a Z position. And we will default the Z position to 0. Set the cell size, and we will set the Z position, and that's it for the initializer. Now our class has one final requirement to satisfy this protocol. We will create a redraw function, and this function will go through every tile in the world. And it will get a sprite name, and we'll use a function we will be creating in a bit. We'll create a function called getSpriteName for tile in the world at tile.key at a specific position. And that's because the sprite name might be dependent on where exactly in the world and what kind of adjacent tiles there are. Also, we want to get a texture, and this too will be a function we'll create in a bit. We'll take get texture named, and we'll bring in the sprite name, and then we will call the final function that we need to create in this for this class. That's a set tile texture, and this one will take a texture at a position in our scene, in the scene we got passed in. So there's a couple of functions we now need to implement. So let's get the sprite name for the tile first. So this will be a private function. Get sprite name for tile in world at position. And this is a vector, and this will return a string. And first, let's make sure that this is a tile we actually have in the world. And if it's not, we'll return just a space or almost an empty string. Also, let's make sure that the tile is a wall, because otherwise we can just return the tile's raw value. Basically, only for walls are we going to do something specific. And this is a lot of code. I am going to copy paste it because it's very, very repetitive. But I will walk you through it. So what we're doing is we're going to be looking at the adjacent tiles. And we have a tile to the north, to the west, to the east, and to the south. So we're looking around our tile. Then we will have a variable called wall string. This is what the wall will be called. And this will always start with wall dash. And dependent on the north, west, east, south tiles, we will be adding specific values to this to the string. So if the north tile is a wall, we will set the north flag, a south flag the same, but then for south, a west one for west, east for east, and so on. And this will give us results that are similar to basically the names of these tiles. We have a tile sprite manager here, and in the end we can return the wall string. So let's see. So we now have a name, a sprite name. Also, we want to get and cache textures. We'll create a private function called get texture named, and this will take a texture name string and return an SK texture. This is intended, these caches textures. And what we're going to do is we'll see if the texture is already in our tile texture map, texture name. And if it is, then we will return the texture. Otherwise, we need to load the texture from disk and store it in our cache. So we'll say let the texture be an SK texture for an image named, and we'll use the texture name. Then we will say tile texture map for the texture name equals the texture. So here we're putting it into the cache, and then we can return the texture. So now we have a way of getting cached textures, and we only need to implement one final function, and that is the set tile texture, and this one is going to do the actual displaying. So we'll create a private function called set tile texture. And this will take a texture, a position, and a scene. And we'll first see if this is on a position that we already have an SK tile map, an SK sprite node for. So we'll look in our tile sprite map for the position, and if it is, then we'll say note that texture is texture. So we will change its texture to the one that was passed in. This is an SK scene. If it's not yet there, then we need to create a SpriteKit node. So we'll create a new node called SK node. It'll be an SK sprite node. It will have a texture from the one that was passed in. It'll have a size, and the size will be a CG size. Width will be the cell size, and the height will also be the cell size. The node will have a position, and the position will be a CG point. X will be the cell size times the position cast as a float. And the same for the Y. We'll have a cell size multiplied by the position cast as a float. And this will have Z position, and that's the one that was passed in to this object earlier. And we will give it some user data to show, let the tile know where it is. This makes UI work later a bit easier because we can then inspect the node, for instance, we click on. And we will add it to the node to the scene, and we will put it in our map. And I think this is enough to show the world styles. So let's start using it in our game scene. So our game scene will need, let's define the cell size on the game scene as a constant. And this will be a CG float. And let's create the tile sprite manager here. That's a tile sprite manager. And cell size will be cell size, and the city position will be 0 for now. Let's also add a camera. This makes moving out in the game world later on much easier, and it makes also doing the initial positioning a lot easier. So we will create a camera node, and because we're going to populate it in the deep move function, we'll make it implicitly unwrapped. Let's see. So we have a did move to view. Let our camera node be an SK camera node. Let's put it at the 0 position, and the scene's camera will be the camera node. And then I want to call a function called redraw, which we'll define right now. So we create a function called redraw, and all this function will do for now is it will call our tile sprite manager and call its redraw function. We also need a world and the scene. Well, the scene is easy, that's ourselves, and the world, we can create a world as part of the scene. However, this is an empty world, so it's not very interesting yet, but I think we should be able to run this. Okay, still the same as before. It's not strange because our world is empty, so I think it would be valuable if our world could at least create some form of sample world. So what we'll do is I'll create a mark here called demo world, and I use these if you're a fan of using the, let's see, always need to look where it is, use the minimap, then you can see these types of marks in the outline. So that's quite convenient. Let's create a static function called make demo world. And this will return the world. It will start by creating a new world. And then in the end, returning the new world. Let's make sure our new world has a room. And to do so, we'll create a helper function called make room that will draw a room from a bottom left position to a top right position, and we'll go from a row in bottom left dot y to the top right dot y, and for a column in the bottom left dot x to the bottom left dot top right dot x, and then we'll check if on one of the walls, so if r is bottom left dot y, or the row is the top right dot y, or the column is equal to the bottom left dot x, or the column is equal to the top right dot x, then we'll say our set tile for the position and the column and the row we will set to a wall. Else we'll set the tile to the same position, but make it a floor instead. So now we can in our make demo world say new world, make room from for instance -5, -3 to 5 and 3. And if we go to our game scene, and instead of creating the world as an empty world, we call make demo world, and we run this, we should now have something slightly more interesting to look at. Oh, here's our world. And you can see that the walls are indeed nice and connected. So we have a world with our walls and we have our floor. That's quite a lot already, but I want to take it one step further, because what we can quite easily do is also uh, visualize how jobs and what jobs will look like. Well, at least we can't really show the job itself, but we can at least see show the effect of the job. And to do that, we need a game loop. And the game loop is basically what makes the game update, for instance, every frame. And to do that, we are going to use our game scene as a sort of conductor for our game loop. And that requires a few variables. We need to keep track of our last update time. This will be time interval. It will start off as 0. We need to define an update interval. This is basically how much time do we want to have passed between every update. I recommend using this to not do an exact update every frame, but at least give it some discrete time. And then we need to take care of how many update delay we still need until basically the next update. So there's an update time interval, and we'll set it to 0 as well. And then we go to our update function. There should be, there is one here already, at least. The basics is available. We'll first calculate the delta time, because delta time is quite useful to have in any case. We'll take the current time and we will subtract the last update time. So that's the difference between this frame's time and the last frame's time, and that will be the time passed between the two frames. The last update time we will set then to our current time, and our remaining update delay we will subtract the delta time. If the remaining update delay is less than or equal to 0, then we will reset it to the update interval, what we'll call world.update, and we'll redraw. To make sure we have something to show, we will create another helper function. It will be almost similar to the make room function, but the big difference is going to be that this one creates jobs instead of setting the tiles directly. And so let's comment this one out, and we'll say jobs.enqueue, create a new job, the job call to change the tile, create a wall. It will have a target position, same as what we had before, and here we'll create walls, and here we will create floors. So this function, instead of directly changing tiles, it will schedule jobs to do so. Then let's use this in our demo world to make it a bit more interesting. So to show changes to the world, we'll take a new job, make room jobs, and the bottom left can be -10 to 6, for instance. And this one can be -4 to 10, for instance. We also need an entity because entities are required to work on jobs. So we'll create an entity. We will name it worker. And the worker can start at position 0. And we'll make sure that the new world.entities is this entity. Let's see. If I'm correct, if I run this, we should start seeing something. That time interval, okay. Typos can always happen. And well, We can't see the worker, but the worker is definitely doing something because the worker is creating this room. So that's, I think that's actually quite cool. It's quite impressive. Let's stop. So to recap, we created our task sprite manager that can show the world. We now have an update loop that shows the world each time at least an update happened and something might have changed in the visualization. Where we're able to schedule jobs and we can see the effect of the jobs happening. We get nice walls that are continuous. All in all, quite cool, I think. Next time, we will add the entities on the screen so we can actually see the entity working on jobs, which is a nice improvement. But for now, this should be enough. Thanks for watching. Have a good day.